Okay, so real quick, we're going to look at, we can take advantage of our product rule and quotient rule that we've learned, and we can come up with some new derivative forms. Like now we can do tangent, for example. How could we use the quotient rule to derive the derivative form for tangent here, to come up with the rule, derivative rule for tangent? What do you think? The only trig derivatives that we know how to do right now are sine and cosine. Okay, yeah, we could write that as a quotient of sine and cosine, couldn't we? Right? So we could say the derivative of tangent of x is equal to the derivative with respect to x of sine x over cosine x, and we'll just apply our quotient rule. Okay, so quotient rule, have at it. First part. Okay, help us out. First part, quotient rule. We got to take the derivative of that quotient. Okay, yeah, low d high. Okay, so what's that going to give us? Well, low is cosine times low d high, so we got to take the derivative of the top. What's the derivative? Help them out. What's the derivative of sine? Cosine. Yeah, just cosine. So cosine x times cosine x minus high d low, right? So high is sine. What's d low? Derivative of cosine, you guys remember? Negative, there you go. Negative sine x over cosine x quantity squared, right? Which we could just write, remember, we can write that shorthand as cosine squared x. But that just means cosine x quantity squared, and we write it that way. Okay, so we can do a little trig stuff here. Cosine times cosine is cosine squared x. Negative sine times negative sine is positive sine squared x. Do I see anything interesting there? Say it again. Okay, no, I can't. I can't do that because this cosine squared on top is not a factor, right? And this is a really common, like one of the most common algebra mistakes that people make. Like, what if I had, let's try with numbers. What if I had 2 plus 3 over 2? I can't cancel those, because if I did, I'd end up with 3, right? Well, is 2 plus 3 over 2 equal to 3? It's not, right? Now that's different from this. What if I had 2 times 1 plus, 1 plus 4, how about? I'll do 1 plus 3 over 2. Can I cancel those 2's? Yes. I can cancel those because that's a factor. It's being multiplied on the top, right? So I could cancel those, and that would just equal 1 plus 3, which is 4. If I didn't cancel them, I'd get 2 times 4 is 8 divided by 2. I still get 4, don't I? Right? So that's allowed, but I cannot do that because the 2 on the top is being added, not multiplied. Okay? All right, so anybody else notice anything else kind of interesting about that, though? What about the numerator? You see anything interesting in that numerator? Say it again. It's equal to 1. Yeah, that's our Pythagorean trig identity, right? Sine squared x plus cosine squared x equals 1. Okay? So we end up then with 1 over cosine squared x, which is the same thing as 1 over cosine x quantity squared. Well, what's 1 over cosine x? No. What is it? Secant. Yeah, it's secant. Yep. So that's just secant squared x. So we got a new rule. We know that the derivative of tangent x is equal to secant squared x. Okay? Okay, got one. We could do the same thing with secant. And then we'll just do this one kind of quickly here. So derivative of secant x, that would just be the derivative with respect to x of 1 over cosine x. Now, we don't know how, at this point, because we don't have the chain rule, we can't differentiate that as cosine x to the power negative 1. Okay, soon we could do that, but we can't now. So we would just have to treat that as a quotient at this point. So if I use the quotient rule here, I'm going to get low d high, which is cosine x times 0, minus top, which is 1, times the derivative of the bottom, which is negative sine x, all divided by the bottom squared. Well, look what happens there. This guy goes to 0. And would you agree I just get sine x over cosine squared x? So what we could do with that is we could break that up into a product of two different ratios, right? Two different fractions. I could call that 1 over cosine x times sine x over cosine x. And 1 over cosine x, well, that's just secant x, right? And sine x over cosine x is just tangent x. And so we come up with another new rule. The derivative with respect to x of secant x is equal to secant x tangent x. Okay. And let's collect all these together then. So turns out there's, we derived these two, but we could have done the same thing for cotangent and cosecant as well. Now I want you to see how these are organized here. If you see how these are organized, it's really easy to remember them. So you could think of this, the trig derivatives, as being split into two groups. You're taking the derivative of the kind of the normal trig functions, and then you've got the co-trig functions, the ones that start with co. Cosine, cotangent, cosecant. If you remember just the left group, you get the right ones for free because there's a pattern here, right? The derivative of sine is positive cosine. The derivative of tangent is positive secant squared x. The derivative of secant x is positive secant x tangent x. Now, if I look at the co-analogs of those derivatives, they follow the same patterns, only they're all negative, right? The derivative of cosine gives us back sine, right? They just reverse each other. It gives us sine, but it's negative. The derivative of cotangent, if the derivative of tangent gives us secant squared, the derivative of cotangent gives us negative cosecant squared. See what it's doing? It's just swapping the secant for a cosecant, and it's making it negative. The derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. Can you see the pattern? So again, if you just know the black ones on the left, you can always infer what the red ones are going to do. And those are all on that. Did I give you the handout? Okay, I've got it. I've printed them out, and I'll show you where it is. If you go into calculus on the handouts, it'll always show up in the handouts for every day. It just shows up as a table of derivatives. So if you click on that, it just gives you that. Okay, and that's our current table of derivatives. If we add more later in the year, we'll just add those to the list. Okay, there's a few on here that we haven't talked about too, but most of those are the ones, like we haven't talked about the natural log derivative yet, but all the other ones we're good with. Okay, and they look a little strange right now because they've got that u prime at the end, but you'll understand what that means here in, like within days. Maybe I should. So what you do with these for now, you guys just know these in terms of x's. So let me kind of explain like one little part of that. So if we'll just do this one as an example. Okay, how does this one correspond with the derivative form above? Well, for us, if we're just using x's, what would this become? If we're saying that u is just replaced by x, what does this become? The derivative with respect to x of cosine x would just equal negative sine x times x prime. But x prime is just dx dx. What's that? What's the derivative of x with respect to x? 1, right? Times dx dx, which is just 1. So it gives you back the same thing you'd have up here. Pretty soon, those u's will have a lot more meaning than that. Okay, like I say, we probably won't get to it until after Christmas, but right after break, those u's will be much, much more meaningful. Let me print these real quick, and I'll just give them to you right now. And remember, all these are in the back of your textbook too. Yep. Okay, so let's just practice these real quick. Just get a real quick little simple differentiation practice. So what about this one here? What would f prime of x be? Let's just practice using these things, and you're going to want to memorize these, just so you have quick recall. You don't have to waste any time thinking about it. Now I've got a sum of terms, right? So I know whenever I've got a sum of terms like that, I can just add up the individual derivatives. I can differentiate term by term. So what's the derivative of negative e to the x? Negative e to the x, right? Because the derivative of e to the x is itself. And the negative 1 is just a constant we leave out front. So I get negative e to the x. And see if you can remember it. What's the derivative of tangent x? There you go. Secant squared x. Done. That's it. Okay, good job. What about this one? How am I going to deal with this guy? Say that again. Product rules. Yeah, good. Product rules. So f prime of x would equal, what's that? How's that going to be? Almost. Negative. Cosecant squared x plus, okay, good. Cotangent x times 2x. And so how would we write that? Well, now this is my own little bias, but this is what I would do here. I would always put the positive term first. So and I mean, it's not that big a deal, but then you only have to write one symbol instead of two. Instead of writing a negative and a plus, you just write, right? And it just seems, I don't know, just after having done tons of math, it just seems like that's an easier way to do it. So this term would go out front. It'd be 2x cotangent x minus x squared cosecant squared x. Okay. And remember, you always want to write constants, then variables, then trig functions, and things like that. Okay. Okay, so higher order derivatives, next issue. All right, we can take derivatives of derivatives, right? There's nothing to stop us from doing that. So if we say our first derivative is what we've just called the derivative, is really the first derivative, we would write that as either dy dx or f prime of x or y prime, depending which notation we wanted to use, right? Well, what if we took the derivative of the derivative? We call that a second derivative. And there's some notational ways we can write that too. Like y double prime makes sense, doesn't it? If y prime is the first derivative, then y double prime is the second derivative. F double prime of x, yeah, makes sense. This is a weird one, right? This is a strange one. The way we would use that using the Leibniz notation, where you're using a ratio in your derivative, you write it as d squared y over dx squared, which is really strange. Where does that come from? I think it comes from here. I think it comes from the fact that you're taking the derivative of dy dx, right? So it's just a reminder that on the bottom it kind of looks like a dx times a dx, right? It's not really, but it just sort of looks like that. So we write it as dx squared. On the top it's d of dy, and so they write it that way. That's where I'm guessing. I don't know why, but it's just that way. And that same pattern, you can see that same pattern all the way down. Now notice that traditionally, once you get past 3 primes, you don't want to write all those primes. It's too hard to read. And then you just put the number in parentheses, the number of primes. Okay? And so, I mean, this is what the nth derivative would look like then, right? Where n is just, we haven't specified. All right, so let's calculate. How about we calculate first and second derivative of this? Okay, so first derivative. Help me out here. Term by term. Ashton, what am I going to get for my first term?
Is that when you multiply? Like
yep.
Divide?
Power rule. Yep.
Okay, so 20x.
Okay. Go ahead. Keep going. What's the next one?
9x squared.
Good.
And then plus. Then is it 2 cosine x?
There you go. Good.
Minus e to the x. And then do you just do the derivative of pi?
Yeah. What's the derivative of pi? No, not 1. How come, Gabe? You're right. Oh. Go with Ethan's answer. That's a good idea. What do you think? Lucy, how come, what was the derivative of pi? What's the derivative of 4?
0.
Oh, well, okay, so what's the derivative of pi?
0.
Yeah, because they're both constants, aren't they, right? Pi is just a constant. Pi, it's confusing because it looks like a symbol, right? Doesn't, but so are numbers. Numbers are just symbols. Okay. But it's a constant, so that one just goes to 0. All right, second derivative. No harder, right? What's the second derivative? What am I going to get for my first term, everybody? Next one. Well, what's that one going to be? Yeah, 2 plus 2 times negative sine x, so I'll just go minus 2 sine x, and this one's just going to stay the same, right? Okay. I could keep going. Now, let's just talk about what would happen if I kept going. If I keep going with this, what's going to happen to those first two terms eventually? They're going to go away, aren't they? Right? Because like if I took a third derivative, this one's going to become an 18, and then the fourth derivative, that term would just go away, right? So power functions eventually just disappear if I keep taking higher and higher derivatives. What about those two? They're going to stay there, aren't they? This last one's going to stay the same always, right? Which is crazy. I mean, that's just absolutely crazy that the derivative of e to the x persists through all. I mean, that's really a bizarre feature of that function. And this one's actually going to go in cycles of 4, isn't it? It's going to be negative for 2, and then positive for 2, and then negative for 2. But yeah, I mean, you'd get, so these two would persist, and those two would be extinguished if we kept differentiating. All right, let's do a second derivative of this guy. So Nora, what's the first derivative? Just a regular derivative of secant, you remember? There you go, secant x tangent x, okay? So first one's piece of cake. Now second derivative, a little tougher. I mean, it's doable, but it's a little tougher. So second derivative. Cahill, what am I going to get for the second derivative?
Would it be secant cubed x and tan x?
Okay, so good. We're going to get secant x times the derivative of tangent x is secant squared x plus, keep going,
X, tan x.
times,
There's more.
yeah. Because it's product rule, right? So here we did first times derivative of the second. Now we've got to do second times derivative of the first.
Would it be secant x, tan x?
There you go, secant x, tangent x, right? Okay. And so if we clean that up, what do we get? Secant cubed x plus secant x tangent squared x. Okay, good. Could we rewrite that in a better way, maybe? Later on, we're going to be doing, I'll go just a little further with this one. We'll see stuff like this a lot in the future. But later on, we're going to want to be doing things like finding zeros of these derivatives for reasons that are mysterious to you right now, but won't be for long. So I'm going to want to be able to maybe factor these things. Okay, we're going to do a lot of factoring of our derivatives. What could I do to factor that? I could take out a secant, couldn't I? First of all. So if I were setting this thing equal to 0, well, there's one thing I could do is I could find the zeros of secant x. There aren't any, right? But I could try to find those. Okay. And that tells me something. Then I'd have to find the zeros of this, but this is tough to do when you have different trig functions in there. Okay, when we're solving trig equations, and we probably need to practice that a little bit. I definitely will go through some of those with you this year. You're going to get a lot better at trig this year. This is tough to do when I've got secants and tangents. It'd be nice if I could have all of the same species of trig function there, okay? So whenever you see a trig function squared, you know that there's a Pythagorean identity that goes with that. I think I went through this with you guys, but I don't remember. If I did, I bet you it didn't have much meaning when I did it. Now it'll have a little bit more. So I'm gonna do it one more time really quick. So we know, tell me if you've seen this and this isn't necessary. We know our basic Pythagorean trig identity is sine squared x plus cosine squared x equals 1, right? That's the one we always remember. Okay. Well, I can get two other ones from that. If I divide both sides by cosine squared, what do I end up with? Sine squared divided by cosine squared is tangent squared, right? Plus cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. So there's another version of Pythagorean identity that relates secants and tangents. Okay, that's really important. If I divide each side through by, that's supposed to be a division sign, divide by sine squared x, what would I get? Well, I'd get 1 plus cotangent squared equals cosecant squared. Okay? Good. So this is the one that we would maybe use, right? We could use the fact that secant squared equals tangent squared x plus 1. And if I go back to this page, I could trade this for right, I'm making this trade, aren't I? Okay, and then now look what I have. And let's just say I were setting this equal to 0 then. Now I've got it factored. I could apply the zero product property, right? I would know that f double prime equals 0 when secant x equals 0, which is never in this case, okay? Or when 2 tangent squared x plus 1 equals 0, right? Well, I could solve that for tangent. Okay, that would be when tangent squared x equals negative 1/2, right? And that's a unit circle issue. Okay. Well, actually, it may not. Yeah, it is. It's a unit circle issue. Is it? May not be, but that's it. I could use a calculator to solve that anyway, right? That make sense? Okay, so then I end up with my answer being tangent x equals plus or minus so that one wouldn't give me a solution either, would it? Because you can't have tangent squared be negative. So we'd get solutions from either. This is kind of washed out. There weren't any solutions on this one, but sometimes there will be, right? Okay, this is one where it didn't work. Point is, these are what I was trying to make here is that putting these in terms of like writing this in terms of either this factor in terms of either all secants or all tangents is a trick you will use a lot. Trust me, that's a good little math trick. All right. I think I was just going to show you this one rather than take you through the whole thing. Yeah. How much time we get? When are we out of here? 20-something? 25. Okay, let's look at an example here where we're taking the derivative of a quotient involving tangents and secants. Okay? So first of all, you guys see I could factor out an 8/3. Factor a 3 out of the bottom and pull the 8 out from the top, and that's kind of nice. Then I've got this constant out front, and I'm taking the derivative of something that's a little bit cleaner. So I'm going to apply the quotient rule. So I've got low d high, right? The derivative of tangent is secant squared minus high times the derivative of the bottom. The derivative of 1 is 0, plus the derivative of secant is secant tangent, divided by 1 plus secant t quantity squared. Okay? Well, I could distribute here, right? And that's going to give me secant squared plus secant cubed minus secant tangent squared. Okay? And here's a good example of what we just talked about. I want to have all the same species of trig function there so I can factor it more easily. So I could trade that tangent squared for a secant squared minus 1. Okay? And that just goes back to this trig identity, right? Tangent squared, if I subtract 1 from both sides, is just secant squared minus 1. Okay, now when I distribute the secant, look what happens. Good stuff starts to happen. Once I get the same species of trig function there, this is going to become a minus secant cubed plus secant. And look, the secant cubes cancel. That's good. And I could factor a secant out of the remaining two terms. If I factor out a secant, I'm left with a secant plus 1. And then look, I've got a secant plus 1 divided by a 1 plus secant quantity squared. So I could cancel one of those factors on the top and the bottom. Everybody seeing that? And I end up with something that's not too bad. I've got my 8/3 that's always been out front. I've got a secant on the top, and I've got a single 1 plus secant factor on the bottom. Okay? Give me 1 to 5 on that. How that make sense? Kind of see how that thing flows a little bit. Do you see the value? And you'll get a chance to do some of these. Do you see the value of that substitution? That's a good one. Okay. All right. So there's my answer. All right. I think that's good for today. I think that's good. I'll put another assignment up for the higher order derivative stuff. You can get a little jump on that if you want to.